Welcome, ladies and gentlemen, to the webinar today about analyzing thermal and mechanical deformations with ARAMIS digital image correlation and thermography. We are recording the stream today and we'll put it later on onto YouTube so that you can review the whole webinar again or share it with your colleagues. There will be a question and answer available in the webinar tool, so please feel free to ask your questions. We will give you answers during or after the webinar. For all participants, we are going to send you a PDF version of the presentation afterwards, so please feel free to share with your colleagues or others. So my name is Markus Klein. I'm working for GOM in Germany as a business development manager, and the webinar today will be done together with InfraTec.
Hello, my name is Sven Wode. I'm from InfraTec, and I'm as well a business development manager for international sales at InfraTec.
So we're going to start with a quick introduction of the companies and what we are doing. So GOM is developing, producing and distributing software for quality control applications as well as for material testing and component testing applications. We are producing complete turnkey solutions for industrial and for, of course, research customers in the areas of coordinate measurement technology and 3D testing applications. We have our headquarters in Braunschweig in Germany and are working together with a distributor network all over the world with in total 60 sites and more than 1,000 metrology specialists taking care about service, support and sales of our systems worldwide. The GOM Group contains today 8 companies and branches all over Europe as well as in the US and in China. At the moment, we are undergoing a continuous growth to over 500 employees in the whole group and looking forward to support you with your applications.
InfraTec is developing and producing as well as distributing high-end infrared cameras along with dedicated acquisition and analysis software as well as tailored equipment for active thermography, mostly for R&D applications, but also for industrial applications where we can also offer some rather turnkey solution or even customized solutions for you. So the specifications of our cameras. We have some cameras which can offer a thermal resolution with better than 13 millikelvin, as well as cameras which can go up to 25,000 frames per second, and high spatial resolution cameras with up to 1920 by 1538 native infrared pixels. As well, we have optics which allows spatial resolution down to 1.3 micron per pixel. To handle all these data either for high-speed cameras or for big format cameras, we also can offer a 10 gig E fiber optical interface for a direct connection to a standard PC or standard laptop. Besides this, we also can offer some spectral filter wheels or filter wheels in general, where you can put in your own customized spectral filters or ND filters up to 25 combinations. Further, for standard cameras, we can offer an option with an optomechanical micro-scanning unit, which is enhancing the resolution up to 4 times. On the other side, we're also offering cameras which allow you to bin 4 pixels to 1 pixel, which allows a much higher frequency per second or frame rate, but as well a higher sensitivity on thermal detection. Besides this, we can also use for most of our cameras an expanded dynamic range using the multi-integration times method, where customized integration times can be defined. InfraTec is located in Dresden in Germany, and our mission is to be a specialist in infrared technologies and offering the best solution and service for our customers. InfraTec was founded in 1991 in Dresden. It's still privately owned. We are about 200 people, and our turnover is more than 33 million euro in 2018, where 60% of this amount is done by international sales. We have two business units. One is a sensor division for pyroelectric components, and the other one is the infrared temperature measurement division, where I am standing for today with our infrared cameras. We have also a distribution net worldwide, and we have 4 subsidiaries besides the German one. We have one in Chesterfield, one in Dallas, and one in Shanghai. If you have any questions later on which we cannot answer after this session directly, you can contact us with the dedicated links you will find below the words chart. Also, you can directly send us an email.
So going a little bit deeper into the technology aspects here, as we are talking about the combination of infrared measurements and digital image correlation, some words to the principle of image correlation. Usually sensors contain 2 cameras, as you see here in the picture, and an illumination device to illuminate the part, the specimen to be measured. What is image correlation? So usually for preparing a test, for performing a test, the specimens need to be prepared with a pattern that follows the deformation of the test part during the test, sticks on the surface and represents the deformation of the part. The patterns are prepared with different materials for different applications. Feel free to, shoot us any question if you have, whether your parts can be prepared and how they basically can be prepared. A main aspect of image correlation is the image acquisition. So a reference image is recorded from the part before the test starts. So the undeformed part is acting here as a recorded reference, if you want so, for all further displacement and strain calculations which are done on the images. During the test, an image acquisition is carried out depending on what the application requires. Slow speed, high speed, so we are working with this on static or on very dynamic tests with specimen velocities of 100 meters per second. It's a question of the camera technique, which is then there used. Image processing is the next step, which will be done with the images. So basically for image correlation, the image is divided into small areas which are analyzed by their gray values. This is done in the undeformed image, in the reference image, left and right. Center areas are identified in these images and also throughout the whole image sequence which is recorded. From these center points, which are thousands calculated in the images, 3D coordinates are calculated, which represents the surface of the part. Due to the issue that the image acquisition is done time-based, velocities can be calculated as well as the 3D displacements of the part throughout the test. A strain tensor is further on calculated through the 3D coordinates, so the displacements between the 3D measurement points is analyzed for major minor strain evaluations as well as strains in X and Y direction. Shear strain can be calculated based on the volume constancy of materials, so usually talking about sheet metal parts. The thickness reduction is a calculated result value as well as strain rates for all of these measures due to the time-based image acquisition.
The infrared camera technique is based on the fact that each object which has a temperature above the absolute 0 Kelvin, means minus 273 degrees C, is emitting infrared electromagnetic radiation. The definition of this infrared radiation is about 0.8 to 20 micrometer wavelength. Our cameras, and usually all infrared cameras, are using mainly the mid-wave infrared range, which is defined from 3 to 5 micron, or the long-wave infrared range, defined by 7 to 12 micron. These both wavelengths are usually, or these wave bands are usually named as heat radiation bands. So the calculation from the infrared radiation which is received by the camera into the temperature is based on the Planck's radiation. So we have a direct correlation of both the temperature and the radiation. So the sketch is showing an infrared camera which is just receiving the radiation and turning these values into digital values which are transferred to a PC. So these cameras are working either in the mid-wave or long-wave range, and the data are used for each pixel by Planck's law to be calculated into a temperature. Also, we can do some corrections within the software, which is taking into attention the emissivity of the sample or of the material of the sample, some reflection from the environment, and also some absorption which can occur between the object and the camera. In this special case, we are looking on materials which are treated by mechanical forces, and each material which has a load of mechanical forces is replying by any heat changes. So this can be caused by a ductile deformation, so it might be grain boundary displacement, damages of the crystal structure and the microstructure, or even crack formation, which will be in the macrostructure, up to a really complete break of the sample. And also we have elastic deformation, which is causing heat as well, but not destroying or deforming the object. Like this example, you apply a load, a mechanical load, and the material will be deformed and generate heat. And when you release the force, the system is cooling down. You see this on the live infrared streaming of a sample which is periodically mechanical loaded by a force, and you can directly see the temperature changing by about 0.5 Kelvin during the unload and loading cycles. We can use these data as well for a special analysis based on login, where we just point out the differences of the temperature under load and unloaded situation of the sample. We also can see this in 3D, just to have an imagination what is the real difference relative to the different positions or locations on the sample. In the next few slides we will see also a stress test analysis, but not with periodically load, but with a one force load until crack.
So today we would like to go a little bit deeper into the issues to combine both measurement techniques together. So combining the results from digital image correlation evaluations, displacement strains, together with the IR temperature data. So what you see in the images at the moment, this is the base data that we are typically using. We use images from the ARAMIS measurement systems, which are black and white pictures with speckles on the parts. We are looking on the InfraTec IR images, so the temperature measurement data, and the question here basically is how can this be combined together to do an evaluation of the temperature on the surface of measured parts. So the main issue here is that the temperature data needs to be aligned with the 3D surface coordinate results. Issues that we see over here is that the ARAMIS system basically provides a certain sampling on the parameters which are set in the measurement project. The infrared measurements also come with a certain sampling on the surface depending on the field of view and on the pixel amount, of course. And the idea is to bring both together, align that together to get a homologous temperature distribution throughout the complete test, even if the specimen is moving. So therefore the idea here is to be able to evaluate the strain or the displacement results at the same time as with the temperatures, and to see where temperatures happen on the specimen and where they move throughout the test. So this enables in the end the separate evaluation of the thermal and mechanical deformations which are going to happen for your applications. So a main important issue is to do the alignment of the temperatures and the 3D surface coordinates. The measurement setup itself, important here is to, of course, set up the ARAMIS sensor on the same field of view as the infrared camera. Another important aspect is that the relative positions of both sensors need to stay constant throughout the whole test. So therefore, there is no motion between the sensors allowed, as well as no motion relatively to the test part. Synchronization is another important topic, so there will be an electric trigger used between the Aramis system and the InfraTec IR camera. So every time the Aramis is taking a pair of images, the InfraTec camera is triggered externally from the Aramis system so that we can be sure that both measurements are taken at the same time so that they can be correlated later on time-based. An application example, as we have seen before on some slides, tensile test here. So the Aramis sensor is positioned in front of the test part as well as the IR camera. In reality, this looks like you see on these images over here. The Aramis sensor here, an adjustable base, is aligned horizontally to the test specimen. You may ask yourself why we do it like that, but the issue is that these cameras do have a 4:3 ratio. From the size of the camera chip and the resolution, so we want to maximize the resolution on the test specimen. The InfraTec IR camera is positioned next to the specimen here, so it both looks on the same field of view on the same specimen so that we then later can correlate both measurement results together. Looking on the result representation over here, some of you might have seen Aramis results already. The temperature will be treated in the same kind of way inside the Aramis software later on. This was a standard tensile test that was carried out with a thickness of 1 millimeter steel with distinct yield strengths over here. That's the reason why you see the generation of the Ludas bands in the center image. The Aramis 12M system was used, just that you can get an idea about the resolution, and InfraTec Image IR 8300 camera is used to capture the temperature distribution from the specimen surface. The main result that we will see in the end is that the temperature data is available inside the Aramis project and can be directly correlated with the strain or the displacement distributions. And thus it's another measure, another result data set which is available for all evaluations. Having a little closer look on the measurement results over here is in the beginning of the test, the elastic phase. The video will start in a few seconds again. We will see some temperature changing, which is going to happen in the elastic range, which is starting now. You see some changes happening due to the generation of the Ludas bands in this area over here. Then the specimen is going through the standard deformation happening before the specimen is starting to neck and fail, where also the temperature distribution starts to localize due to the high load on these local areas. A further application example, of course, also in component testing. We do have the same kind of requirements to do these tests. The sensors need to be aligned both on the same areas. A difference here, of course, is that the test specimen's geometry is completely different. So we talk about a quite curvature shape over here, which is of course typical for component testing applications. And an important issue to use these two measurements together here is to do the alignment in a proper way so that the temperature data can be oriented on the real surface of the test part. Here we would do it with a CAD data set, basically to map the temperature based on the coordinates of this data set. So therefore in Aramis the CAD dataset is imported together with the temperature export from the InfraTec software. There is an alignment which is typically done based on 3D coordinates so that then the temperature data is available in the object's coordinate system and can be evaluated together in the same way as we have seen before. So the temperature data here is shown on the top image and the major strain results on the bottom image. So therefore, both datasets can be evaluated together and used for further evaluations. So thank you very much for the moment. We will stay tuned for another 15 minutes. So if you have questions, please feel free to use the question and answer tab. We're sending you this presentation a little bit later on so that you can review. And again, thank you for your attention.
Also from me, thank you for your attention and looking forward for your questions.